reliability in different aspects. And his research interests include quality and reliability engineering and product analysis and modeling analysis. And actually, he's a very active researcher, and in the past many years. And something that really amazes me is he always maintained his high energy level. And that's true, right?
I don't know for how long.
I still remember many years ago, I was lucky to become his student, and I looked at him. He actually looked exactly the same as today.
Oh, thank you very much. Look at that. You are not very straight anymore, right?
I'm afraid. So probably in the next several years, we're going to look at the same age. That's something I'm really worried about. Well, without further ado, let's welcome Dr. Elsayed.
Okay. Thank you, Tao. I'm very pleased to be here. Congratulations for the 20th anniversary. This is a great group, and I'm happy and lucky to be part of this group. So the title here, at least in the workshop, says QSR 20th Anniversary Celebration Workshop, Past, Present, and Future. So I'm going to focus on the future. So I will not talk about what I did and what I'm doing. I'll talk about what I'd like to do, and I've done some of it, but most of it will fall on you. So I want to, hopefully, by the time you finish this presentation, will open opportunities for research topics of importance, or what I think of importance to the society. So you can see over the last few years, the biggest advances in technology today is due to few things. New materials and new sensors and ability to communicate and software. So new products come into the scene almost every day. And people worry after the product's designed, the design engineers say, well, what's the reliability? Well, reliability has never been up front of any design process. It's always the last thing, but think about it before they market the product. So I'm not surprised I'm the last presenter today being a reliability fellow. So the point is, indeed, that is reliability, as important as it is, it doesn't come up front when people design systems as such. Come in a short time, we have a product, we need to check its reliability. Why? We need to provide warranty. We need to worry about, we need potential failures and so on. So with that, I am going to shift today. I work on I'll give you an example of cases. I wanted to talk about autonomous vehicles. Are going to come in the market in no time. In about 2-3 years, we'll see them. So how reliable are they? So how do you measure its reliability? Big question mark. There is sensors to collect data. There's a processor that does the image analysis. There is the decision making, and there are parts of the vehicle. A vehicle now is going to experience more miles because it is autonomous. You can send it back over to do other jobs. So over a 3 years period of its life, will have as many miles as you have in over 10 years. Can you predict the life of the components 10 years down the road? So there is issues, many of this in the products we do every day, and with the new technology and new material, we see that. But another topic that came to my attention, which I'd like to share with you, so it's reliability and modeling, testing, and prediction of artificial human joints. I didn't know much about medicine, and the only thing I know about medicine, I go see my doctor once a year for an annual checkup. They never see me again. It's once a year, and that's what I do. So the look at systems in general. When they're complex, you're going to take a flight, and there's a delay. You have no idea what the delay is. But there's an entire system that runs that aircraft. There is issue with the aircraft itself. There's issues with communications. There's issues with the reservation system. There's issues with the luggage handling. But all of these, you want it to be on time to take off at certain location. If you are delayed a few minutes, your upset system is not reliable, the airline is not very good, and so on. But it's a big, complex system. There's many things going into it. Same thing with the human. The human body is a complex system. Not only complex, there is lots of dependency among components of the human body. So years ago, about 4 years ago, I was contacted by a company somewhere. Somebody referred them to me, and they have an artificial heart, total artificial heart. And the question was, we need help from you to let us know how we test it, because we want to get FDA approval. So I said, well, you tell me more about this artificial heart. I cannot give you the details of this heart. It's a venture capital, big company in France, and an agreement with them not to give details, but I can tell you in general what I did. So they wanted to see, the FDA requires that this is a temporary heart. It's placed in a human body for 1 year until a donor is found. When you place a heart in a human body, you never want to see it out again, right? Until the operation time to replace. So there is no failure of that unit. So they want to test that heart and prove that when we design it and build it, it's going to survive this duration. So I started learning more about it. It has two pieces in it, two sub-assemblies. One is called the prosthesis, which is mainly the main heart that goes in the human body. It has all diaphragms and other elements. They never share this with me. That's their secret-like. And the other part is the wearable item, and that's where the patient wears these. There are batteries and pumps and a control unit that collect data, and that's one that controls your heart rate and the blood flow. So the first part is, once you place it in the human body, you have no control. So you worry about reliability of that. The outside part, the wearable part, is repairable, replaced. You can get a new battery, you can replace that. So that one has availability issue and much easier to handle than the inner part. So this one, the prosthesis part, is a reliability issue. You design it for a certain reliability by the end of the period of 1 year. Well, because we know reliability is the decrease in functional time. So at the end of this period, 1 year, to reach certain reliability level. And they expected the reliability target about 0.9 mean life of 83,000 hours, 10,000 hours about 1 year. That's about 8 years if it continues to run. So they need also confidence level around that. So how do you test that? Well, I do accelerated testing. Among the products I do, I design a test plan, I do accelerated condition, develop mathematical model based on the physics idea of how the failures happen to predict what happens at normal conditions. So how am I going to stress the heart? So imagine you are going to go for a stress test. And the doctor said, well, run a stress test for you. So I put you on a treadmill and you keep running. How does it affect your heart? So imagine if you, instead of running or stress for 15 minutes, well, he forgets about you and they keep running for another hour or two. How does that affect you? Is it stressing the heart? What do you mean by this? So imagine you are a runner and you keep running forever, never stop. Will your life be shorter? Why stress? Is it a stressful heart? So that became the questions where I struggled with. What do you mean by stressing the heart? So to avoid these issues, spoke with the designers and said, well, really, this is planted in a patient who is simply waiting in hospital, and we observe him until we find a heart replacement. So let's look at the profile of the patient during the time. And so this is what I try to do. So this is the what's happening here. Okay. This is the system and availability. It is the system and availability because there are two pieces together. One is repairable and the other one is not. So we multiply both of them to estimate overall system and availability, and becomes a steady state over the period of time. So it will go up to 115,000 hours. That's about a year and a half or so of work. So the profile of a person who is sick or waiting for a heart, the system is non-repairable. It's placed in the human body. So we look at the time and the duration for that. So the activity is sleep, and they tell you what time it's about. The duration is about 10 hours, and the flow rate of the blood is 5 liters per minute. The heartbeat at normal conditions is 77 beats per minute. And you follow that during the rise, a walk, and you can see the change in the heartbeat and the amount of flow blood needed as you perform activities. That's a typical profile of a person. So, of course, this is a normal person who's waiting for a heart replacement. Now, you can see if a person, every one of us has a different heart rate, more or less. Athletes have a much lower heart rate in general. It's about maybe 50 or 60 heartbeats per minute. Mine is especially low. It goes down to 42 or 41 about. And occasionally it goes down to 30. But anyway, the others who are heavyweight, a person at risk, sitting, doing nothing, but in excess weight, his heartbeat is about 100 beats per minute at rest. Is it stressed? So become an issue with when you use the heartbeat and stressing the heart to increase the heartbeat and the flow rate and so on. So we actually had to do prototypes of this unit, 4 prototypes, and we run a test. So I'm not going to describe the details of the test. And we count when it will fail, these components, and we can repair it and continue the prototype testing. Of course, in the human body, when you place it, then you're not going to do any repairs. But we did that for the test plan purposes. We used the FDA requirements for classifying the failures. So catastrophic failures, this is really result in complete loss of the capability of the system and literally can lead to death. The other one is critical failure, the failure of the system to perform safely. It cause some injuries or death, if serious enough, and then marginal failure, and minor failure when the battery needs a replacement or a change. So we designed a test plan for them and use sequential testing. We look at the number of failures observed, that's cumulative test time, and we see created boundaries for them. And we can tell when you reach so many number of operating hours without failure, you're going to meet the requirements. So if we test success, if no failures during 51,600 hours of cumulative test time, we passed the test. So FDA looked at the test plan in details, and they approved to go ahead and conduct the test. So that intrigued me. I don't know much about human hearts, and I'm not my specialty. I said, what about talk about complex system and humans? What can I do as an engineer? So I looked at the aging of humans. So if I looked at the average age of human since 1880 or 90, and I actually plotted it, and you see the dotted red line is the actual numbers, and they fit a regression model straight line. I have a slope with 0.18. That's the number of years extended in human life per year. If there is no medical intervention from advances in medicine or technology, that's just straight line. So projecting that, And about year 2100, about 80 years from today, the expected life would be about 100 years. Well, imagine you're living to 100 years. What happened to all these components in the human body? Well, components means your heart and your lungs and your kidney and liver and joints. They function continuously. I mean, heart never stops, right? And same thing applies to your lungs and all other parts. Do they wear out? I mean, will eventually fail? They will. So what do we do? So I became intrigued in the subject, but I tried to avoid the cell and tissue issues, and I looked at the joints. Joints are mechanical components, nothing but material to pieces or connected together with a hinge like socket and the cup, and they work and they function. So actually I can create a mechanical part to do that job. And actually that's what they do. They do artificial human joints. So if you look at your joints in the human body, there is single joints and there's multiply connected joints. Single joints are your knees, your hip, your ankles, your fingers. Multiple connected joints are your spine. There are many joints that are connected. They have a different failure mechanism. So I started learning why do these things fail? Why do the joints fail? Then what do we do about them in terms of reliability? I'm looking at the human as a machine, and if I do a replacement, I make sure that is reliable. So the joint replacements essentially can relieve pain, increase function, and usually it minimizes the orthotic or damaged joints. We replace it by a new one. It's called prosthesis. This is made of usually metal and plastic or plastic. That's where you come in as an engineer. What do I do there? Hip and knee replacements are the most common joint replacement. The surgery can also be performed in ankles and other parts, elbows and so on. So if you look at the hip replacement is nothing but you have a cup or a socket, you have a ball, and this will act as a hinge. That's here. That's the area to give you motion here. And this is a stem inserted in your leg, and this is inserted in the thigh, cemented, as a cement layer. So that gives you the motion and control. So there are many, many operations run every year. And many companies make these joints, except they fail. So if you look at the failure and the revision, it's significant. It can go up to 10%. People go back the joint replacement and need to replace it again, and multiple times. And there are many reasons for this. So it's a high percent revision rate. Why can't you design it, you build it, you insert it once, and sign a lifetime warranty? Don't come back. Can you do that? Of course you can. And that's what they think. It can be done. So the goal of the work you could do is, can you improve reliabilities of these? There is no revision. It's a costly process. For a patient, it's a painful process. You have to go back. For a society, you are paying more and more for the same operation. So I looked at what companies do. There's a company in New Jersey, it's called Stryker. They make joints. There's a recall for a joint. I can't recall your car, but I'm recalling you. Come back. We need to replace your joint. That's a painful process, right? So what happens? The lawyers in the region jump into this. We'll sue this company. We'll get your money back and more. And everybody has this kind of socket come back. So it became another problem. So they use this as in hip replacement, recall their femoral head. It is the ball. And the specific recall components intended essentially the ball at the top of your femur or the thigh bone. This head is an artificial hip socket, and it causes a problem. If it wears out, the wear-out material or debris goes in the bloodstream, goes around the area, and cause infection, literally could lead to death. That's the problem with this. Wear out of all these joints. So the company recalled all of these, and here is the analysis of why things fail. Fracture of the stem itself, the one you put it on in the leg, or the metallic debris resulting from metallocytosis in the blood, which can cause bone and tissue death around the area. Lost range of motion of the hip. You do this and you can't move after operation. Or you make noise as you walk and playing music with your knees. God knows. So, or loosening the impact due to insufficient fixation. When you put the hip in place, you have a cement that holds the socket in. It fails. Why? The remodeling of the bones. The bone change, the growth, and start breaking the areas. Excessive wear, pain and inflammation, hip dislocation and joint instability. And that is, if you walk, nothing is aligned and there is instability in your walking. And the fracture of the bone at and about the implant. So I'm going to, when you do reliability work, you just don't collect data and look at the hazard, the function, and get reliability function. You need to know the cause of failure. Now, making your model is more realistic, because if you know how to model that and capture that in the model, it will be more realistic in estimating the life of the unit. So here, what medical communities, the best they have done is post-operation. They collect data. So many patients went through this surgery. There is 1,000 people went at the beginning of the test, of the period they observe them after operation, and they see how many succeeded, still working, some left, and some how many failed, number risk at any time, and they use Kaplan-Meier approach to do that simple survival curve. There's no prediction, there's nothing guarantee about these units. I built it, I inserted in your knees or your hip, and I'm going to observe you. Well, if it fails, I recall you, but it's too late. As a patient, when you go for heart surgery and tell you, we'll get you a new artificial heart, we ask them, what is the expected life? Is expected life a good measure for you? Tell you it's about, 2 years. That's a mean life. Would you insert something critical in your body that you have a mean, only you know about it? Mean is 2 years? Of course not, right? Well, the mean could be between 0 and 4 will give you a 2. Right? If you put it in, fails right away. So they use different measures for that with the time to first failure. When you have a batch of units produced, when will the first unit fail? So same situation here. Are already implanted and observe the time and look at the time when it fails. Well, it ends up to be a curve that has no value. This is your reliability function. I don't know much with this. It's 15 years of study, and they end up showing how the people behaved at the survival function. It doesn't tell you much. So you need to know, if you want to design a new hip replacement or knee replacement, you need to know the cause of failure or failure modes. The first one, septic loosening or instability. This happens, the joint become loose. It happens when you call aseptic means there is no bacteria causing any infection. Assume that's called aseptic. So bone remodeling around the area due to stress shield. Stress shield is when you have this metal inserted in you and they carry load. The bone doesn't carry as much load, so the bone that weakens, doesn't have mass density, become viable for fraction. And that causes the loosening of the joints. The infection due to implant failure, it's a common side effect when you have a replacement. Surgery is actually you have a bacterial infection, and what happens, it creates a film on the implant, which then becomes resistant to antibiotics. No treatment. You have to go back and replace that. So another one is wear out. So if you have a socket and a ball and rotating, depends on your motion and your weight, in amount of debris is a function of the material you have and motion you have exerted on that. That amount of wear out with the no lubrication or others depends on the material used, the contact stresses, the lubricants and the clearance, and surface hardness and the roughness. When you have a regular surface, like a ball, it is not exactly a ball, and you put in a socket, and wear out, the wear out is non-uniform, not uniform. Some areas will wear sooner than others, and the load distribution changes continuously. Wear out changes with time, and then there is oxidative wear, which is the corrosion. It depends on the material you're using. Titanium alloys, stainless steel result in increased wear rates as compared to ceramics, cobalt, and chromium alloys. So I have a ceramic, and ceramic is actually the most common one, except if you fall, you're going to fracture it. It's pretty material. So people try to avoid having ceramics of ceramics. Stainless steel paired with so steel with polyethylene produce higher wear rates because you have steel, hard material, polyethylene, softer material, have a wear out. And ceramic on polyethylene produce the lowest rate of materials. So you need to avoid the debris. So one of my students, Tim, they came to visit me. He's about now 50 plus. And the summer before last summer, he was having a hip problem. So he came to visit me a year later. I said, Tim, how's your hip? I said, I have a replacement. I said, how is it going? He jumps up. I said, you see, I can, no problem. I said, how do you know that there is no debris wear out? He said, I go there once a year. They take a sample of the blood around the area, see if there is any metal around the area. So the wear out is a concern on all these designs. If you make a joint and doesn't wear out, ideal, right? So the failure time distributions is an issue because all these failure modes don't happen at once. They happen with delayed time in between. So when we do failure analysis and do reliability modeling, we collect data, we do the mathematical model, but if you have a competing risk, any one of them will happen, and they happen at different times, there's a delay time. There is no mathematical model today that will exist to capture the effect of the failure time distribution of the joint as a function of all these. First one fails, second one fails with a delayed time, tau 1. Tau 1 is a random variable. It isn't a constant value. And times F3, third failure mode, times T minus tau 2, it's another random variable, problem becomes complex. There's no, forget about even the joints work I'm presenting. If you want to go mathematically solve this problem by itself, it's be a challenge. So you do convolution, and you take, here's an approximation, you take every pair at a time and do convolution, and then convolute the next one, and so on. That's one way. I have no solution for this problem, by the way. This is the future, so I don't have answer for that. So we can do this. We say reliability of any units are connected and they compete in failure modes. We call it, competing failure mode mechanisms. So reliability is the product of all reliability of individual cases. And you do the same as I mentioned to you. And you worry about looking at the convolution of reliability functions or PDF if you have enough data. Now, that is not as bad as the next one, multiple joints. So you have multiple joints, and every one of us, as you age, you'll get shorter. Why? The natural behavior of the spine discs, they hydrate. They shrink in size. When they shrink, and naturally become brittle, which makes them more prone to damage and rupture. So you can have growth of the bones and herniated disc. As the disc becomes dehydrated, they shrink further and lose height and can render your spinal column unstable. Collapsed discs can also lose their effectiveness as cushioning. They don't absorb anymore. So we could have a degenerative disc, and they cause the degenerative disc disease. That's what medical profession refer to. Not that only, because as your discs become less effective in controlling the movement of your spine, your facet joints on the discs will actually be forced to compensate, will carry the load. As a result, the small joints can become pressurized. There's high stress, high pressure in the joints. By doing that, you're overloading it. Your excess movement can cause the protective cartilage linking between the two, then break, creating another painful friction and bone-in-bone contacts. So what happens? In an attempt to stabilize your facet joints, your body may produce protective bony deposits, will create bone spurs. And a common side effect of bone spurs is painful spinal nerve compression. The point is, your damaged spinal disc can strain the vertebrae above and below it. It propagates. So when you have a degenerative disc, it isn't isolated one. It propagates with time to one above and one below. By doing that, you are going to reach a point where you have to change to make a change. Means a disc replacement. So when do you do that? Well, I'm talking to, by the way, this is not all my work alone. I've been talking to spine surgeon and joint surgeons for some time. So when do you do replacement of the disc? I said, well, I asked him, I said, what do you think? I said, well, when the disc becomes degenerate and gets, crushed like, collapsed. He said, no, we'll go and replace that. It isn't the one that's causing the pain. It could be the one next to it. He said, we really don't know. So his answer to me said, don't ever have a surgical disc replacement and his spine disc. He said, you can work on the 7 discs in your neck. We know it very well. Beyond that, we don't. Right? So that's a problem because they are interconnected. They're dependent. So here what happens in the spine disc. It starts somewhere and keeps with time, propagates. Until you reach a point where the threshold level comes, can't move anymore. Time for operation. So what is the threshold level for replacement or change? I don't know. So that took me mathematically to a problem. Imagine you're measuring the degradation or degeneration of a disc with time. So at the time 0, you're okay. Time passes, the first disc degenerates. At a certain point of time, it actually propagates the pain or degeneration to the next disc, disc 2. The first one is getting worse, still degenerating. The second one, after some time, degenerates to the third one, propagates. Second one is still processing. This is a degradation process, a branching degradation process. There's no work on that. The best work I've seen in the branching degradation processes of Brown motion up to called terminating propagation process. After only one time terminates, other one begins. But there is no study, there is no in the statistical literature or any literature that does branching of degradation processes. So if you don't want to work with any spinal disc, it's a theoretical research problem. And you can formulate it, I give it an attempt here to do some work with. There is again, there's a time delay between even these. So you can say the first disc, degeneration of J, disc J, at time t, it has a certain initial value, or it could be 0, And mute has a mean value, and again, it's a Brown motion process. It has a diffusion parameter and Brown motion coefficient. At interval 2, this is the first one continue to degrade, and the second one propagates, and you keep adding cumulative one of these. Mathematically, I don't know yet the formulation, but these are thoughts of potential problems to be addressed. Well, so where do you go? As engineers and people, many of you ask them what you do. I said I'm doing 3D printing. Very good. Here's the chance. Do 3D printing of this material. Okay, here's what I'm going to tell you. So we do 3D printing. So I'm going to take you through the theoretical modeling of this, which I explained some of that. You need derivations and mathematical modeling of reliability before you do any of this work. Second, you need to know to actually make a product, a joint replacement. Third, you need to test how long, how many samples, and then eventually, when you make a unit, you're going to say, this is a unit and no revision. It's perfect, right? That's what we could do. So if you look at what the joints we have, these are typical joints. This is currently available in the market. Metal on metal, perhaps the worst. And metal on poly is okay, except you have a wear out in polymer. We have ceramics in poly. This is better than just metal in poly. Less wear out. And ceramic in ceramic, it is really no wear out, but the fracture when you fall due to brittleness of the ceramics is the problem. So I did some work on meniscus, knee. So that area in your leg, or your knee, I mean, it actually, this is a work done with the medical doctors where they form the company and make meniscus replacement. Meniscus is you make a scaffold and you insert it in the knee joint, and hoping the tissue will go around it and the fiber with time will get more but degrade in the system. So here's a meniscus we built, and we created a machine. It's a continuous fiber to do that. The problem is, the issue is, or what I'd like to carry further is, it's not only one type of fiber. Imagine you have a spool, and the spool has fibers in it. It's all fiber. But the first 100 feet of that fiber is high strength. Second 100 feet is a medium strength fiber, and so on. So I can put the first 100 layer, followed by the second layer. I can give you different properties on the same cushion. So I tried to come up with a pattern idea and run an issue with the medical doctor, so I didn't pursue it. But so here's the typical machine we built, a prototype. We put the pins to mimic the exact meniscus, and get the head and get the fiber, and we weave, continuous weaving through that to create the pattern we want. And you can see this how it's being weaved. It's all continuous. You cannot have a cut in the fiber. We come up with different designs. So I'm not going to bore you with this. So 3D printing, this is a continuation of that. Now imagine you have a spinal disc. So the 3D printing of hollow stems. The stem you have is metal, and because of problem in the bones, deformation, and because the bones get remodeled, they don't grow, they cause loosening and become an issue. Imagine that stem is made of hollow material, but high strength, lattice type. You could actually reduce the stress or increase the stress in the bone become active and don't lose strength. 3D printing, complicated structures such as stems with different porous designs can be manufactured. In these, it can introduce porous into orthopedic implant that brings two benefits. It reduces the stress shielding due to the stiffness mismatch between the metal and the bone, and indeed allow bone ingrowth of firmer fixation. So here is a desk. And this is a project we tried to do. You get the spot that, I don't know what disk number this. This is the lumber, disk 4 from bottom. This is the geometry. To do it in 3D printing, I don't want to duplicate it as a solid piece. I really want to be innovative in the design. Do people who work in 3D printing? Imagine you have an athletic person who is a basketball player, and I don't want to replace this with a solid piece. I want to actually create multi-layers. One layer have high strength, other one has a cushion, absorb shock, a different layer with different properties, so I can create multi-layers with different properties. I want to create a unique desk that meets that person's activities. So imagine you look at this. So we dissect, we slice the desk, layer by layer, and look at the geometry. And you can go up to 600 layers with this. And every layer is different. This is 90th layer. This is vertical. This is still slicing. This is 110th layer, what it looks like. This is geometry. This is the 50th vertical, so we go in vertical and slice it how it looks like. So you can actually slice it in horizontal and vertical directions and do exact geometry. Now, the material choice become a challenge. What material to use and how you deposit it. And problem with the polymer and 3D printing, the different characteristics of the layers. Polymers tend to have high expansion coefficient. So I have made a part that has 3D printing for a different project, and I have metal pieces inserted in it. And what's close to the source of heat, because I'm heating in the medium before it goes in, all of a sudden they were press-fed, or the metal pieces was press-fed into the polymer. With time, all of a sudden my metal pieces are falling off from that material because the polymer expanded and does not hold. So there is lots of thermal variabilities. If you put different layers, you got to know how they behave with each other. So these are, again, vertical slice, different location. And you go on, and here is what the geometry looks like at the end, multi-layers. And you can give you a steel file. You go ahead and produce it. Well, what material, what layers, that's what you do. Everybody, most of you saying I'm working 3D additive manufacturing. Produce this one, right? It's a challenge, right? In fact, the geometry, if I want to create scaffold with one string, with one fiber, I can create different patterns. Which one of this pattern has a high strength? There's no optimization. I don't know how to optimize it, but I can come up with different layers, and every layer has different pattern geometry. So, problem with 3D printing, as you know, the problem is the anisotropic behavior of material. If you have a piece made of metal, such as steel, you take pieces and you do tension on them in one direction, take other piece horizontal and you do tension, same yield strength, no variabilities. If you do this in 3D printing, lots of variabilities from one layer to the other. If you take a vertical piece or horizontal piece, that causes lots of strength properties variability. So if you take it in one direction or other direction, you'll have different curves, never the same strength. When you put 3D layers of metals, once you put a layer, it's a molten layer first, and you put the second layer, if you wait for a fraction of a second, oxidations happen. And layers will never be uniform. So if you want to do testing with these, whether it's a fatigue test and so on, more likely to get cracks. How do you minimize the impact of that? So 3D printing, people promising too much, but material end has not been done yet carefully to address that. Indeed, here's the different material. This is looking at the stresses, and this is the strain. This is typical when you take a material and test it, plot a stress strain curve, and you look at this different material from This is different 45 angle, flats. And look at the material, they change, and the properties, that one goes in one direction higher, the other direction lower than the other one. That's the issue we have in 3D printing. So this is from medical journal, and here what the summary of this. Jacques Adam and others, they say there is an extensive body of literature that reports potential new bone-related materials, but these products and their surgical implementation suffer from substantial technical, surgical, and manufacturing shortcomings. More importantly, you couldn't tell with their performance with time. No reliability estimates. So people have joints, have all kind of material, and you tell them, give me a warranty policy on that. None exists. When will it fail? Nobody knows. So I think you can play a role in reliability. What do? You test. Make samples, make products with expertise in 3D additive manufacturing, expertise in statistical modeling, and reliability. You can come up with new material, new joints that will have longer life than what we have today. So let me summarize this here. Am I done almost? Okay, summary. Even if you didn't, gain much out of my presentation, at least you know there is a change in your body with age, and your bones are going to change, and you're going to be shorter. Sorry about that. And so you can model the degradation phenomena, even just ignore being human joints as such. The reliability estimates of branching degradation, there is no work in the literature in this area. 3D printing of multi-layers with different properties, a very challenging problem. So which layer to go? So what I personally envision, if I have the capabilities to do this, I will create, you have a socket, you have a ball. This is a hip replacement. The wear is a problem, and the debris is an issue. So I'm going to create a surface for both areas, the ball and the socket, that's wear resistance. There's material today it's a thin layer, one wear resistance, will never wear out. Or will have a small wear out, followed by layers of ability to absorb energy to give you the cushion you want. You can put polymer in between. You can put another layer with different types of material, depends on the activities that the person is performing. You can do all this analysis. So in mechanical engineering field, they do finite element methods, and they can help you in choosing the type of material, and eventually you can design it. But ultimately, you must test and then get an estimate of the expected life, and when it will fail, and failure modes you're going to see, and learn from that to make a better joints. So I think reliability testing, modeling, prediction, or provide lifetime warranties will be a way to go. If I live long enough to do that, I'll do it. But so I'd like to thank you very much. I wanted to bring to you what I see the future that you as a community can play a role. I'd like to thank you very much for your attention. Thank you. Thank you. I'm done sooner.
We have a couple of minutes for questions.
Well, thank you very much for the very insightful talk.
Well, thank you.
So I'd like to hear your comments regarding how to systematically link the product design, manufacturing process, and the reliability modeling for this is highly personalized implantable medical devices. And in particular, I'd like to know a little bit about whether we could really mimic the working conditions of these implantable medical devices in the reliability test.
Okay. Thank you very much. Well, I'm going to respond to the last piece of your question. When we run a test or we run any reliability testing, you need to know the condition where that unit is going to be operating at, what temperature range, what pressure range, and so on. When you insert something in the human body, you have fluids, you have acids, you have alkaline environment, you have other environment, and you need to know that. And I know nothing about it. Sorry about that, but the doctors will tell you this. And that's something I'd like to explore personally. But you can actually create the same fluid conditions if I know what it is, and you run through that. We do this in many other applications. If I run it through, some kind of lubricant, I can do that under these conditions. So, but to ask me what it is, I really don't know precisely, but I'm sure the medical community will be happy to work with you on defining that. Companies, there is huge, or a large number of companies, they make joints and make living on this. And you can see what this company recalls the joints. You don't want to be one of the patients that being recalled, going back to replace your hip replacement you just made. So I think I'm trying to initiate some discussion with companies to come on board and say, well, that's the kind of work we're interested in. It's a long-term research, and we learn from it. Now, go back to design and manufacturing and reliability. The unfortunate thing, as I mentioned before, reliability always comes last, right? And it should become at the beginning in the process. And when you design items and other components, if you know something about reliability of these components, you change the design stage before you come back at the end and you test this. So that's what I think the reliability should come up front. So I worked in Bell Labs years ago, and we're looking at components for fiber optics cables and so on. We get the failure data of the components, and we do the analysis before actually putting the design together. And we know if you put this component or this component, your failure rate will be as such. So we go back and redesign it, and we do that and feel, well, failure rate of the system as a whole will be good. We go into manufacturing, and then we do testing and reiterate. Hope I answered your question. Okay, thank you.
Any other questions?
Okay.
So that concludes this keynote speech, and the final words. Actually, in reliability engineering, they talk about aging, degradation, fatigue.
That's correct.
Those words actually do not apply to you.
Oh, thank you very much. Look at this. Look at the compliments of Mr.
Somewhat.
Okay. I apologize for boring you. Thank you. Thank you. Thanks for that. Thank you.